Here are graphs of the Vasicek and Cox-Ingersoll-Ross under comparable parameters. You have to be a little bit careful in doing the modeling, of course, because the standard deviation, the coefficient of dz in the two models is different. And so it's always a question of, well, how do you actually model them with the same parameters? Well, they're both modeled with the same A and B values, which define the mean reversion, and same initial value of 5% initial rates. In order to get the volatility to align, in the Vasicek model, we have a fixed vol of 2%, and in the Cox-Ingersoll-Ross model, we use a sigma value of 2% divided by R, so that we can then have an initial volatility that's comparable. So it's always a little bit complicated to determine how to calibrate the volatilities between the Cox-Ingersoll-Ross and the Vasicek. While they have the same, identically the same drift term, the volatility of Vasicek is a constant. The volatility of Cox-Ingersoll-Ross is a constant times square root of R. So the way the authors circumvented that problem is, in the Vasicek model, we'll assume 2% volatility. And in the Cox-Ingersoll-Ross, this should be a square root of R. The constant term is 2% divided by the square root of the initial interest rate, 5. In other words, what this does is this makes the numerical value of the coefficient of dz equal at time 0, because when I multiply this value by square root of the initial R, I get the 2% the same as Vasicek. But of course, over time, there's no way of stopping Cox-Ingersoll-Ross volatility from depending on R, and there's no way of making Vasicek's volatility depend on R. So we're kind of stuck. The best we can do is to calibrate the two models so that initially they have the same volatility, knowing Vasicek stays constant and Cox-Ingersoll-Ross does not. And you can see here that in this low volatility environment, we get a pretty comparable term structure for zero coupon bond rates. And they're quite similar. But notice that when we raise the, by the way, the Sharpe ratio is also 0. Notice that what happens when we increase the volatility to 10% from 2%. I noted earlier that the Vasicek model had the property that longer rates tended to go to 0 and become negative when you have a large sigma. And we see that here. Again, this is a typo. This should be that the Cox-Ingersoll-Ross was the volatility of Vasicek divided by the square root of the initial interest rate of 5%. And you can see the Vasicek model predictably is producing longer interest rates, an inversion in the yield curve of spot rates where it declines. So if there are any shortcomings in the application of the models we looked at, they're related to the number of parameters the user has to fix. So if you look at these models, we have at most 3 or 4 parameters. We have an A, a B, a sigma, and a constant one way or the other, phi or phi bar. But there's either 3 or 4 parameters in these models that the user can set. What is typically done is that these models are calibrated to market prices. In other words, the coefficients in the model, the A, B, sigma, and phi, are determined in such a way that these models reproduce as many market prices as possible. Given that there's only 4 parameters, one expects that if you were going to reproduce prices, you could reproduce at most 4 zero coupon bond prices. Another approach is to determine those 4 parameters in a way so the collection of spot rates or the collection of zero coupon bond prices match all market data in some measure of closeness. So you look at all the prices from the model, all the prices in the market, and you set your parameters to minimize some measure of the distance between all those. So those are your basic choices, but obviously either one of them will be inadequate to accurately price all market instruments. We can either pick 4 to price and the other ones will be approximate, or we can optimize the parameters to price all bonds as closely as possible in some optimization modeling approach, and then live with the fact that in either case our model is not accurately pricing all of today's marketplace. We're going to now look at some additional models later in this chapter which introduce additional parameters, and the purpose of these additional parameters will be to allow us to calibrate our model to all the price data in the market.